In the third video of the topic collisions, we finally get to collisions. In this video, we'll be looking at collisions and impulse, and also the law of conservation of linear momentum. A collision is defined, as by Halliday, Resnick and Walker, as when a large force acts on a body over a short time and suddenly changes the momentum. The change in momentum is equal to the final momentum minus the initial momentum, and we call this the impulse, J. We also know from Newton that a very small change in momentum, dp, is equal to the force acting over a short time frame, dt. If we integrate both sides over that time period, we get an expression for the change in momentum during that time interval, which is the final momentum minus the initial momentum, which we have defined as the impulse. So we can also write that the impulse is equal to the integral of the force applied over the time period it was applied for. And it's very often in this case that we don't really know how the force varies with time, but we do know the average force of the collision, and also the time over which it was acting. So our expression becomes that impulse is equal to the average force applied multiplied by the time period it's applied for. Before we start to look in more detail at collisions, we need one more puzzle piece. And so we return to linear momentum. In the work and energy topic, I spoke about isolated and non-isolated systems, and I used them to show such things as the law of conservation of energy, which is one of the fundamental principles of physics. So this might seem like something of a contrived situation to have an isolated system, but it isn't really. So just as we can choose a coordinate system of our liking to make solving of our problem easier, we can also choose what constitutes our system. So as with the coordinate systems, the aim in choosing what makes up our system is to make the problem solving as easy as possible, or as simple as possible, while still correctly analysing the physics. And for this, the simplest case is to say that all the objects we're investigating are contained within our system. And for the whole time period of interest to us, nothing leaves or enters our system. And when we do that, we say we're working with an isolated system, and in general this makes our problem solving much, much simpler. In isolated systems, we can work with the properties such as the conservation of mechanical energy, the conservation of energy. In every system, there are two types of forces. There are forces acting among the particles in the system, so these are called the internal forces. And there are forces that change the amount of energy inside the system, and these we call the net force or the external force. So here I want to look at the case where we have a system and there is no net force or no external force acting on the system. So that is that our net force is equal to 0. We also know that our net force is equal to the rate of change of the momentum. So if the net force is 0, then the change in momentum over time is also 0. And this is the law of conservation of momentum. So it says if no net force is acting on an isolated system, the linear momentum of that system cannot change. If we're working in more than one dimension, then we can further specify this law to say that if there is no net force acting in a particular direction, then the linear momentum of that direction cannot change. And this is helpful to us in a similar way as the conservation of mechanical energy, in that it allows us to figure out the results of a collision without knowing the details of the collision itself. And that gives us a handy problem-solving tool. So here we have a system of particles all moving every which way with every kind of velocity. Using the conservation of linear momentum, we know then that the initial momentum, the total initial momentum, must equal the total final momentum. So that is, the sum of the momentum of each of the particles must be the same for the system in its initial state and in its final state, which we can either write as the sum of the momentum of each of the individual particles, or we can say that the momentum of the center of mass of the system must be the same for the system in its initial and final state. And that's really all there is to it.